Calorimetry is the measurement of heat energy, or the enthalpy, that's associated with nearly every single chemical reaction or physical process that happens. Many times you would use a calorimeter to measure this heat. This is based on heat capacity or the specific material no. Calorimetry is the measurement of heat energy, or enthalpy, that's associated with nearly every chemical reaction or physical process. When you're measuring this heat, or measuring this energy, you're not measuring it directly from the reaction itself. You're using known materials and measuring the change in temperature. From the change in temperature, the mass of the known material, and the material itself, you can determine how much energy was transferred from the reaction or the process into that material that causes a temperature change. Thermodynamics, in terms of chemistry, relates to the different energies associated with chemical reactions. These can be things like the spontaneity of a chemical reaction, the general amount of chaos or disorder, or the heat associated with the reaction. Calorimetry is a way to measure this heat energy and see the actual numerical value. The term for heat energy is enthalpy, and pretty much every process, either chemical or physical, would have some sort of heat or some sort of enthalpy associated with this. Energy is required to perform a task, or in the performing of that task, energy is released. It's moving someplace. So if a process or a reaction is endothermic, that means it takes in energy from its surroundings. The total amount of energy for the reaction increases, but it removed it from the surroundings. That means the surroundings would decrease in temperature. So an endothermic reaction typically lowers the temperature and feels cooler to the touch. An exothermic reaction is the opposite of that. It's releasing energy. And when a reaction releases energy, its overall amount has decreased, but that energy still has to go somewhere. And it goes into the surroundings, and that causes the surroundings or your hands or whatever's near it to increase in temperature. The amount that the temperature increases is related to the heat capacity. Each individual substance has a heat capacity, and the heat generated from a reaction is transferred from one place to another. And when you increase the energy, increase or decrease the energy, that's related to the overall temperature. The heat capacity is the specific energy required to raise 1 gram of a substance by 1 degree Celsius. So it relates energy, the heat energy of enthalpy, and temperature. In science and chemistry, the unit of energy is joules, but an older unit and that can be seen and is used in specific circumstances is the calorie. So The calorie is an old unit. It's defined as the amount of energy needed to raise 1 gram of water by 1 degree Celsius. So the definition of a calorie is exactly the heat capacity for water. And one of the constants that you probably should be possibly memorizing for lecture would be the heat capacity of water, which is also how to convert calories to joules. This would be 4.184 joules per gram per degree Celsius. Where you may have seen calories before is on food packaging and food labels. On food labels, the nutrition information lists the calories, and these are the actual energetic calories that you can measure in a lab setting. But the one difference they do is use calories with a capital C. And really what that means, what that indicates, is that these are kilocalories. It only really works for in related to food, but for some reason they do use kilocalories and abbreviate them with a capital C in the word calories. In other countries, I think particularly in Europe, you may also see the calorie count on food packaging listed as kcals or kilocalories. When you're measuring the enthalpy, that heat energy, it's related to 3 different things. So the heat capacity of the specific material, the mass, and the change in temperature. So each different material has its own unique heat capacity. This is, again, the amount of energy needed to raise the temperature of that substance 1 degree, to raise 1 gram of that substance by 1 degree. It goes to show that if you have more material, you will need more energy to increase that temperature. So if there is more mass, it will require more energy to increase the temperature. Last is the change in temperature. This is final minus initial. You're seeing how much increase in temperature did this substance undergo, so you could figure out how much energy was input into the system. You could also determine if you have a set amount of energy, you're inputting a specific amount of energy, how high will the temperature get? This is, again, based on the specific heat capacity of the substance and the amount of the substance. To raise the temperature by a farther amount, to increase the temperature more, would require more energy. So in a typical enthalpy calculation would be something like this. How much energy would be required to raise the temperature of a 250 gram block of aluminum from 20 degrees Celsius to 57 degrees Celsius? So first, you're looking at these 3 things: the heat capacity, the mass, and the change in temperature. Aluminum is a pure substance, and it has a heat capacity of 0.897 joules per gram per Kelvin, or degrees Celsius. Heat capacities can be found in a number of different tables, either on the web or in a lecture textbook, and they're pretty well defined, especially for the different metals and different elements. The mass is given in the problem of 250 grams, and the last component is the change in temperature. You're increasing the temperature from 20 degrees Celsius to 57 degrees Celsius. That is a change in temperature, final minus initial, of 37 degrees. So when you multiply all of these three things together, you end up with the answer of 8,297.25 joules. This is how much energy exactly would be needed to raise the temperature of a 250-gram block of aluminum from 20 degrees Celsius to 50 degrees Celsius, 57 degrees Celsius. This is the amount of energy that is added into the aluminum, but it has to come from somewhere. So it's coming from the surroundings. If you're adding temperature, you're removing it from someplace else and transferring it to the aluminum so that way it increases in temperature. Enthalpy is very direction-based. So when answering questions, either in lab or in lecture, it's very important to read the question carefully to know what is it asking for. Is it asking for the energy related to the reaction or the energy related to its surroundings, what you would feel if you put your hand close? And the numerical value is the same, but the sign would be different depending on where you're looking. There are a number of different types of calorimeters. Some measure the heat associated with a reaction based on a titration or the slow addition of the other reactant. Others scan across a full temperature range to see the difference in energy compared from one substance to another. And others are adiabatic, which means all of the energy is contained within the calorimeter itself, and there's no transfer to the outside surroundings. Things like a bomb calorimeter are a very advanced way to do this. This calorimeter is very heavy and the heat capacity is very large. All of the energy from a reaction inside this calorimeter is absorbed by this calorimeter itself, and the change in temperature is measured. As you get simpler and simpler, the calorimeters themselves still operate in that same way. The energy from the reaction is transferred to the calorimeter or the water contained in a calorimeter, and the change in temperature is measured. While a bomb calorimeter is an expensive calorimeter that is very adiabatic and very little energy is lost to surroundings, a very simple calorimeter is just styrofoam coffee cups. Based on the material of construction, styrofoam, there is very little heat that is transferred into the calorimeter or into the styrofoam itself, and therefore very little heat is lost to the surroundings. Calorimeters are devices that measure the heat energy or enthalpy of a reaction or a process. So a calorimeter is something that has a very well-known heat capacity, and many of them are adiabatic, meaning there is no loss of heat, no loss and no gain of heat, and all of the energy is contained in the calorimeter. Adiabatic is a theoretical term for that, but for the most part, all of the energy is contained. And the reason for that is a lot of it will be absorbed by the calorimeter itself. So if you know the heat capacity of the calorimeter, or at least of the different components of the calorimeter, and measure the temperature change, you can calculate the individual heat, individual enthalpy associated with that temperature change for each of the different components, add them all together, and then that would be the energy that was released from the reaction and absorbed by the calorimeter itself. If you go to advanced classes, advanced labs in physical chemistry, you would use what's called a bomb calorimeter. And this is the setup that would also be used in the simulation. So a calorimeter like this has predefined walls and it's filled with water. Water, again, has a very well-defined heat capacity of 4.184 joules per gram per degree Celsius. So you would accurately measure the mass of water inside a calorimeter, have a reaction occurring completely submerged in the water in a smaller vessel. Any heat associated from that reaction would be released into the water, and the temperature of the water would increase. When you go through the enthalpy calculation of the heat capacity times the mass times the change in temperature, that would be the enthalpy that was released by the reaction in the calorimeter itself. So, typical example, a calorimeter consists of 300 grams of water and a 150 gram container of aluminum, both of which are at 20 degrees Celsius. A reaction occurs inside the calorimeter of a 10 gram sample, and the temperature increases to a final temperature of 66 degrees Celsius. What is the enthalpy of the reaction? So you don't know what the sample is. You're given a mass, but you do know the mass of water and of the calorimeter, as well as what they are. They're two pure substances, water and aluminum. So first thing, you're looking at each component separately. So the temperature change overall goes from 20 degrees to 66 degrees, a change of 46 degrees Celsius. So the energy absorbed by the water would be the heat capacity of water times the mass of water times 46. So overall, the water in the calorimeter absorbed 57,739 joules. The aluminum has a different heat capacity. So the heat capacity of aluminum is 0.897. It's a different mass of aluminum, so times 150 grams, but the change in temperature is the same. The whole unit, or the whole calorimeter as a whole, increases in temperature by the same amount. So when this reaction occurs, the bulk of it was absorbed by the water, but some of it also was absorbed by the aluminum. That means the total energy absorbed by the calorimeter was both of these added together. So that's how much was absorbed by the calorimeter. But where did that energy come from? The energy came from the reaction that was happening inside. That means the reaction lost this amount of energy. So this amount of energy, this 63,928, that was removed from the reaction itself. So this has a negative value or a negative direction in relation to the reaction, but a positive value in relation to the calorimeter. Again, you need to make sure to carefully read these questions to see what it's asking about. Is it asking about the calorimeter, how much is absorbed, or is it asking how much is coming from or being absorbed by the reaction itself? So you can also get the enthalpy per gram. The example lists a mass of 10 grams. That means that for every 1 gram of substance, there was 6,392.8 joules of energy that was released from the reaction and absorbed by the water and the calorimeter. While you can measure in lab the enthalpy associated with different reactions, you can also theoretically calculate the enthalpy or the heat associated with a reaction based just on the balanced chemical equation. And to do that, you can look at all of the different bonds within all of the different components and all of the different chemicals. So on the reactant side, you can imagine every single bond has some energy associated with it. In lecture textbooks and online, there are lists of bond energies, the amount of energy contained in each of these chemical bonds, either a carbon-hydrogen bond, an oxygen-oxygen bond for molecular oxygen, a carbon double bonded oxygen. All of these have a different energy associated with them. When a reaction occurs, you can imagine all of the bonds in the reactant side need to break and then reform into all of the products. To break a bond requires energy. So this is how much energy is required, 414 kilojoules. That's how much energy is required to break a carbon-hydrogen bond. This is also the amount of energy that's released when a carbon-hydrogen bond is formed. So by looking at the total number of bonds in the products and total number of bonds in the reactants, you can calculate what the overall enthalpy for a reaction would be. So in the case of a combustion reaction of ethanol, burning ethanol in air, in oxygen, you have one ethanol molecule will react with 3 molecular oxygens, and that gives 2 carbon dioxide molecules and 2 water molecules. So these are shown with every single bond specifically drawn out. On the reactant side, bonds that are broken, energy is required for these bonds to be broken. There is 1 carbon-carbon bond at this energy. There's 1 carbon-oxygen bond. There are 5 carbon-hydrogen bonds, 1 oxygen-hydrogen bond, and 3 oxygen-oxygen bonds. These are from the 3 separate molecules of oxygen. So these are all the bonds that in theory are breaking. And you add those up, it requires a total amount of energy to be absorbed. Oops. In the case of the combustion reaction of ethanol with molecular oxygen, you're burning ethanol in air. It's 1 molecule of ethanol will react with 3 molecules of oxygen to form 2 molecules of carbon dioxide and 3 molecules of water. This is the balanced chemical equation for the combustion reaction of ethanol. All of the bonds I have drawn out specifically just to visualize each and every one of these bonds. So on the reactant side, there is 1 carbon-carbon bond, 1 carbon-oxygen bond, 5 carbon-hydrogen bonds, 1 oxygen-hydrogen bond, and 3 oxygen-oxygen bonds. There are 3 molecules of oxygen. They each have 1 double bond, so there are 3 of them in total. So each of them require that bond energy to break. So this is how much energy is input into this reaction in order to break all of these bonds. So the reaction itself absorbed 4,735 kilojoules of energy per reaction, or per mole of reaction. Moving on to the product side, this is energy that will be released when a bond is formed. A bond is at a much lower energy than the individual atoms. So there are 4 carbon double bonded oxygens, 2 molecules of carbon dioxide, but each one has 2 of these same bonds. So there are a total of 4 carbon-oxygen double bonds. And please note that if you're looking through this and looking at carbon dioxide, the bond energy of the C double bond O in carbon dioxide is particularly strong. So it does have a higher energy associated with it. There are also 6 oxygen-hydrogen bonds from the 3 molecules of water. So overall, there was a total of 5,953 kilojoules of energy released from this reaction. That means overall, the amount of energy was leaving this reaction, so the direction is negative. Adding these two together, you have a positive number and you're adding a negative number, so really it's subtraction. The net energy associated for this reaction is negative 1,218 kilojoules. It is an exothermic reaction. This reaction releases energy, and therefore the temperature surrounding it will go up. This amount of energy right here, this negative 1218, it is leaving this reaction, so it's negative, but it would be gained by the surroundings. It would be gained by your hands if they were closer. So the temperature is increasing of the surroundings. This experiment uses an online simulation of an adiabatic calorimeter. That is a calorimeter where there is no heat lost or gained from the outside surroundings. The calorimeter itself can be found at the following website. When you first access the website, you're taken to an overview page. There is also a Learning Outcomes tab, which shows the different learning objectives utilized in this simulation. Under the Experiment tab, there are 2 choices: Run Demonstration or Run Experiment. The first part of the experiment is utilizing this demonstration. You'll be walked through different steps in how to utilize this simulation, selecting different components and mixing them together to measure the temperature increase. Through the simulation, you're going to perform 4 different interactions. You're going to be mixing 2 portions of the same substance at different temperatures and see where the heat is transferring. Where is energy going from one side to the other? You're also going to add a solid metal with a known heat capacity and a specific temperature to a different mass of water. This is transferring heat and getting you used to using the enthalpy calculation. You're also going to dissolve salt in water. This gives a heat of solution, the energy required to break some of the bonds holding the molecules together, those intermolecular forces, and break them into individual ions. And last, you're going to be mixing hydrochloric acid and sodium hydroxide to give you a heat of an actual chemical reaction. For the remainder of the experiment, you're going to use the Run Simulation option in the simulation. This lets you choose the different components, mass, and temperature that you will use in both the beaker and in the calorimeter, allowing you to mix and match things. In the second part of the reaction, or the second part of the experiment, you're going to be looking at the heats of solution of different salts. You'll weigh out different salts at different masses, all at a constant temperature of 20 degrees Celsius, and add that to a known volume of water, or a known mass of water, also at 20 degrees. Any change in temperature from that solution is a result of breaking the intermolecular forces holding the solid salt together and dissolving it. You're going to go through and look at each of the different chloride salts listed under solids: sodium or lithium chloride, potassium chloride, calcium chloride, and sodium chloride. And you're going to measure the heat of solution and molar heat of solution for each of these 4 compounds. So in this step, you're looking at different compounds, measuring the molar heat of solution for each of them, and going through selecting the solids and the liquid water. To measure and calculate these heats of solution, you're taking first the total enthalpy that was absorbed by the calorimeter. This is the enthalpy using the mass of water, the heat capacity of water, and the overall change in temperature. This gives you the total numerical value of the enthalpy that, or of the heat that's being released. So again, using the enthalpy calculation. All of that energy that was absorbed by the water left the salt itself. That energy was released from the salt. So in relation to the salt itself, it is a negative enthalpy value. Then to find the molar heat of solution, you have that heat of the reaction, that negative enthalpy value, divide it by how many moles of salt you actually used in the simulation. You can choose any mass of salt that you would wish, because this molar heat of solution is a constant value for all of them. So the mass of salt that you weigh out, you will convert to moles, and then use that to calculate the molar heat of solution for all 4 of the different chloride salts. The third part of the reaction looks at the chemical reaction of acids and bases. So in this part of this simulation, you're selecting different acid solutions and choosing volume and concentration, and reacting these with different base solutions. Again, choosing a volume and a concentration, and going through and measuring the amount of heat that is generated in this reaction. The bulk of part 3 looks at the investigation of the acid-base reaction with hydrochloric acid and sodium hydroxide. This will be done in 3 different reactions, each involving 2 separate processes. There is the process of the solid sodium hydroxide actually dissolving, and there's also the process of the hydroxide ions reacting with the acid ions. In reaction number 1, this is very similar to just what you did in the second part of the simulation. You're looking at dissolving solid sodium hydroxide in water and calculating what is that molar heat of solution for sodium hydroxide, just to take the solid and dissolve it in water. The second reaction is a combination reaction. You're taking solid sodium hydroxide and reacting this with a hydrochloric acid solution. There are two different steps or two different processes happening when this action is performed. First, the sodium hydroxide is dissolving. That does require energy, and there's an enthalpy associated with that. After that's completed, the hydroxide ions are reacting with the H+ ions, also generating heat and having an enthalpy change. So this experiment has both of those things combined. The third reaction takes a sodium hydroxide solution and reacts it with a hydrochloric acid solution. In this case, the sodium hydroxide has already dissolved. That heat or that enthalpy associated with dissolving sodium hydroxide is already taken into account. That already happened in this, however they made the sodium hydroxide solution. Now, in this step, the only reaction that's happening is with the sodium with the hydroxide ion and the H+ ion. In all of these three reactions, be sure to take into account the limiting reactant. So you need to know that sodium hydroxide and hydrochloric acid react in a 1-to-1 ratio. Therefore, it would be easy if you had the same number of moles on one side versus the other. But if not, you need to base your calculations on whichever the limiting reactant is. The fourth reaction is kind of a repeat of the third one. So in that one, you particularly looked at sodium hydroxide and hydrochloric acid. In the fourth reaction, you're choosing any of the strong bases to react with any of the strong acids. These are the strong bases that are available in the simulation, and these are the strong acids available. You've already looked at the combination of sodium hydroxide and hydrochloric acid. So you need to choose any other combination of a hydroxide, strong base, and a strong acid, and looking to see what is the molar enthalpy of that reaction as well. The at-home portion of the experiment involves looking at a food item. You can pick any food item that you have at home so long as it has a nutrition label. The calorie content listed on the food packaging is the energy associated with this food. While food calories are 1 kilocalorie, that is 1 food calorie equals 1,000 science calories, that can also be converted into joules. And what you're going to do is look at the bond energy associated with the energy process in the body, the process of glycolysis, and determine how much energy is needed in 1 mole of glucose and how much food you would have to consume to obtain that amount of energy. The last part of the experiment involves you at home finding a food sample with a nutrition label. So the foods listed have the unit of calories. These calories are actually kilocalories. You'll notice that every time they use the word calorie, it's a capital C, or at least it should be. 1 food calorie is equal to 1,000 science calories, or 1 kilocalorie. Some international foods have the calories listed as kcals. The calorie itself is based on water, where the unit is defined as the energy needed to raise 1 gram of water by 1 degree Celsius. So the calorie itself is the heat capacity of water, 4.184 joules. So in this experiment, what you're going to do is find this food sample, see how many calories there are, and record what the serving size is in grams. You're going to convert the number of calories listed on the package into the unit of joules, and then convert that to joules per gram. So you're using the serving size, you're figuring out how many calories there would be, or how many joules there would be in 1 gram of your food. Then you're going to use the glycolysis slide that's found on Blackboard to see the energy and enthalpy that is involved in the process of glycolysis, which is how your body generates energy. This is the glycolysis slide found on Blackboard. There is 1 molecule of glucose that turns into 2 molecules of pyruvic acid, 2 molecules of water, and 1 of the hydrogens ends up being bound to a carbon on an NADH molecule. The rest of the molecule remained constant. So what you're going to do is figure out what is the enthalpy of this reaction, and then utilize your food sample to see how many grams of your food would be needed to undergo 1 mole of this reaction. Overall, in this simulation, you're looking at heats of solution, or the heat associated with the process of ions dissolving in water, as well as the heat associated with an acid-base reaction. You're doing this in a simulation, so you're doing this in a completely theoretical adiabatic calorimeter. No heat is exchanged with the outside surroundings. This is theoretical, and really in all calorimeters, even things like a bomb calorimeter, there would be over time some heat exchange with the surroundings. But as you're doing it in a simulation, you're going to look through these couple of different processes. You're going to measure the heat associated with them and look at the molar heat capacities, or the molar energies associated with those different processes.